Thank you, Alicia. Thank you. I would like to thank you also the organizers for setting up this program. It's always very nice to come back to KITP and for the opportunity to present our work on superconducting quantum links, which is a first step on the study of retarded interactions. So we got very much interested when I landed in Spain. I landed in a theoretical physics group that was interested in how quantum particles can get correlated in relativistic scenarios. And so one problem is how can a quantum field mediate an interaction between two objects that are sufficiently separated that the information from one takes time to carry to the other. Part of this is this so-called Fermi problem, where you have one atom that emits a photon, and the question is when will the other atom get correlated to that photon? And so we started looking at emitters in waveguides. At the time, there were also people were developing, like for instance, Alejandro, effective master equations for these systems. One thing we found in the very simple problem with one excitation is that indeed there is a light cone, and before that light cone, you don't have any entanglement for these kind of systems. After that light cone, if you wait long enough, you have a dynamics that can be described by a master equation with coefficients that include coherent and incoherent interactions. But before that, there is a nice entanglement process that depends on the separation between both particles. At the time, it was just a curiosity. I mean, normally we are not looking at this regime because the separations that you need to have for that are very large, or the delays must be very long. But recently, we entered a scenario where this is becoming possible. So what I'm going to talk about is related to a European project called Superconducting. It's already finished. It was coordinated by Peter Ravel at the time in Vienna. And it all started with this setup in Zurich, where they took two dilution refrigerators, each of them hosting a superconducting quantum processor, and they connected them with a quantum link, basically like a microwave waveguide. The time separation wasn't very large, it was 5 meters, and during the project, things grew, and then we managed to have this very nice experiment where they had a 13-meter long link. You see here the pictures with, I think, 5 concentric cubes.
Just a quick clarification question. In the picture before, what was the initial state?
Which one? You have one emitter, one excited atom. This is the Fermi problem. You excite one atom, the photon is emitted, and how this guy correlates with the other one. And so now you have this setup where you have 2 or more qubits on each fridge, and they are connected by a microwave, 3D microwave waveguides, operating at 10 to 20 millikelvin along the length of the device, which is really amazing. I mean, this is a very big device, and it's really at nanokelvin temperatures. This experiment has been used in Andreas Walrath's group to demonstrate violation of inequalities between qubits hosted at different fridges. So that's possible because the delay between these two devices is quite large. It's 100 nanoseconds, and you can host 1 to 2 photons propagating at the speed of light. That means you can do measurements in a time that is shorter than for information to travel classically between both devices. So that's a very nice scenario. But that means we already have access to a very interesting physics of retarded interactions. This is not the only device. There were previous experiments by Andrew Cleland and other groups, superconducting circuits, with also waveguides. You also have these very nice experiments in China that either explore extremely long coaxial waveguides, 64 meters. In this case, it's only in the same fridge. Or you can have multiple qubits connected to each other with cables. Like here, you have 5 processors connected to each other, and people have been exploring how they can be interacting and exchanging information one with another. So the usual way that people address these systems is with this approach of quantum state transfer, where you basically take this idea proposed by these 4 big guys, which is not too difficult to understand. Basically, you have 2 quantum systems connected by a photonic medium, can be optical or microwave photons, and you design 3 steps. One is the transduction of information from a qubit to a flying qubit, and then the process of, after propagation, of reabsorbing it in another quantum system. And this can be done in many quantum optical systems. This was shown by Rempe in Max Planck in 2012. And what I'm going to talk about is how we can model this for superconducting devices, including realistic modelization of the problems you find in the way. It takes you to a framework of quantum networks. You have connected quantum devices, and now with this idea, you can design protocols. You can design how you exchange information, and you use these primitive of moving a qubit from one side to another as part of a quantum algorithm. It's interesting, but I find it a little bit limiting. In fact, we have a much richer scenario. This is a very new type of physical system. It's a many-body system. You can have many-body systems with separations that are macroscopic. These are objects that interact through the exchange of photons. Those photons have very long delays. We can engineer those delays. And those delays, they are now a new timescale in the problem that competes with other things. But for instance, the local controls react on the different qubits. This is not a Hamiltonian system, but still a coherent system. And it would be very interesting to explore the potential of this kind of setups. For instance, you can find that if you have different delays, you can induce frustration because of the interaction of one object with different neighbors. You can engineer gauge fields. You can do many things with these kind of devices. But we are not yet there. So we are still modeling the connections between those devices. This is what I'm going to talk about. The thing we do is basically to try to find a realistic model for the waveguide that connects both processors. Basically find a good Hamiltonian with a good description of the spectrum and coupling strengths. And then we either use static normalizations in the limit of few photons, up to 3 photons we could do, or we try to do some operator equations, Heisenberg-Langevin equations that we can approximate in some regimes. If you take this equation and you project it again to a finite number of excitations, you will again get models that can be analytically tractable, or at least numerically. So what I'm going to show is basically based on the 2 ideas of that paper. One is that when you control the coupling of the quantum system to the waveguide, you basically engineer a photon that then fits the dynamics of another quantum node or quantum qubit or whatever you want. This photon, we are going to engineer it so that it can be perfectly absorbed by the system. And how do you determine that the photon is absorbed? Well, simply by looking at how this system, qubit 2, influences back into qubit 1. These are all retarded interactions, but you can look for conditions where the photon that is emitted back by the second qubit perfectly cancels the part of the photon that was emitted by this guy and returns back. And this is called the dark state condition, and they give you nice designs of these controls of the coupling between the qubit and the waveguide. That is an ideal scenario of really where you couple qubits directly to the waveguide. Unfortunately, that's not what we do. We have to model because the experiments are slightly more complicated. In the experiment, people try to shield the qubits from the waveguide by having some resonators, filters, so that you can detune the qubit from the filter and isolate it from the waveguide. And that way you can control the information that is here, protect it before you want to transfer it. So it's a slightly more complicated system, but we have a very well-defined shopping list of things that we have to model and engineer theoretically. And that list is more or less like this. So first, we need to control how a qubit injects energy into the waveguide. We need to shape that energy in very well-defined wave packets. Then these wave packets will propagate, and we need to be able to reabsorb them in the receiving node in a perfect way, with as high fidelity as possible. And once you have this primitive, you can use it to create entanglement, and you must optimize it for it to be useful in the lab. So let's start with the first one. This is just a remark for theoreticians. This model seems very simple, but it has a lot of technical details that one has to carefully address to make it accurate. For instance, once you put your cavity connected to the waveguide, you get the renormalization of the properties of the resonator. You get a line shift. This line shift has to be very accurately estimated, otherwise you don't get any good results from here. The dispersion relation is not linear, that we will have to also to take it into account. And then there is a funny thing, which is that we are working with waveguides that have different lengths. They can be either very short, half a centimeter, very long, 30 meters. And in all those scenarios, the resonance frequency of the qubit with respect to the modes of the waveguide becomes extremely relevant. So all of what I'm going to show you comes from a perfect calibration of the resonance of the qubit and the cavity to the modes of the waveguide. If you detune yourself from those, even though we have this input-output theory, there will be a boundary of fidelity that you can achieve in those devices. And you will see that. So once you calibrate these things adequately, which you have to do numerically, and the lab is not a problem, the renormalized frequencies are all the things that you are going to measure, you can now explore how you can inject energy into the waveguide and get a perfect depletion of the qubit by controlling the coupling between the qubit and the cavity in this particular scenario. So we have a tunable coupling between this will be a transmon qubit and an LC resonator. And well, that works. Basically, we have different ways of controlling this coupling. We can do it both in amplitude and in phase. In both cases, what we have is a cascaded system. The qubit injects energy into the cavity, that injects energy into the waveguide. And so you can model it in the limit of one excitation with these equations and do a wave packet engineering. So basically, you tell me the shape of the photon I want to inject. I know the dynamics of the qubit, and from here I get the coupling of my system. And that's a very easy process that we can analytically do for certain shapes of pulses. Interestingly, we are not limited to having just the width of the cavity, which was the original design. We can make the pulses broader in time, which is narrower in frequency. And we can also do other things like to tube pin to compensate the frequency, move away from the resonance of the cavity, and other improvements. So it's both amplitude and phase control. Interestingly, I mean, this is a curiosity, but all the wave packets that we have to do, they have to fit in the bandwidth of the cavity. That means that the logarithmic derivative is bounded, so you cannot do Gaussian pulses. They have to be hyperbolic second at most, and that sets a limit on what is the maximum bandwidth you have available for this state transfer, which is crucial for our designs. Well, okay, in the experiment you can have more than one cavity to improve the filtering and the protection of the qubit. We can repeat this process and also do the inverse problem in this scenario, but that's not very relevant. What matters is what fidelities can we achieve in this case, because we now have the possibility of injecting a photon, and we now have to design the opposite control here to reabsorb it. Turns out if the wave packet is time reverse asymmetric, this other control is simply the time reverse of this one. That's not the only possibility. If we have, if you give me another wave packet, we can still find out the computation, what is the control we need to perfectly reabsorb it, and will become relevant later on. But in this scenario, what happens is you excite the qubit here, you activate the coupling with the cavity, some energy transfers to the cavity, and it goes into a propagating photon, and is later on reabsorbed in the second node. These are the two controls, which in this case they are identical because the two nodes are identical as well. You can change the width of the photons, you can make them longer, and then in this case the controls are slightly different from the usual hyperbolic second. You need to leave the cavity open, and you can take a limit where really the emission and the absorption of the photon are not distinguishable. This is a very weird limit, because in this limit the bandwidth of the photon is so narrow, at most one or two modes are participating in the dynamics. And in this limit, we are not usually doing this kind of description. One would take a qubit, a cavity, another qubit, and do the dynamics of the full system. But still, this theory works. This is an exact simulation of the whole problem, and this gives you, well, you don't see here the numbers, but it gives you perfect state transfer in this very weird limit. So what is going on? So basically, if you change the length of the waveguide from very long to very short, you have somehow this kind of infidelity of the state transfer, where you have this very weird limit where photons are much longer than the waveguide, and a limit where the photons are shorter than the waveguide. And the transfer, more or less here, is almost perfect. It would be enough to build a quantum computer. And after some threshold of the bandwidth, begins to be deteriorated algebraically. So basically, what is happening there is the bandwidth of your photon is increasing as you make cavity decay faster and faster, and suddenly your photon is exploring the curvature of the dispersion relation in the waveguide. So your waveguide is not, it's a three-dimensional structure with a band gap at zero momentum, so you begin to see this curvature. But on the other positive side, we have here this extremely good fidelity of transfer that we derive with this input-output theory, analytical pulses, and not really thinking at the system like a single cavity. To compare with other protocols, here you have in very ugly plots, but basically this curve here would be the limit where you have only one cavity, and you replace the waveguide with a cavity, and you try to do perfect transfer, and you find some times where you can really get very good transfer of the photon. That's not very useful, it's very slow. There is an intermediate protocol like here where you do stirrup with a single mode of the waveguide. This is what Andrew Killian demonstrated experimentally. And then you take these protocols that we have designed with the continuous limit of the waveguide, and they are faster than anything you can build. And that's true even in this limit where you have 1, 2, 3 modes participating, which is very nice. So it shows that this technique is scalable to all possible designs. And except for this, it would be the ideal way to design this state transfer. So what else can we do now? Well, we can improve. We can make it, we can correct this part where you had a lot of infidelities because of the growing bandwidth of the photon. Essentially what is happening there is you send the photon and initially it's very compressed, but as it travels through the waveguide, it broadens. And as you let it bounce back and forth, it becomes very obvious that it's getting distorted. How can we fix it? We can fix it because we have control of the coupling between the qubit and the cavity. And this control includes not only amplitude, but also phase. So we could try to fix preemptively the distortion that the photon is going to suffer, doing like kind of a lens where we know that we are going to get a distorted photon, and we can design this control to absorb this photon, or you can try to pre-distort this photon so that when it reaches here, it has the adequate shape. In principle, you can do both things. You can both engineer this control and this control to do half of the compensation. And when your waveguide is very long, that's actually what you have to do. And this is indeed working very well. So this will be the state transfer fidelity for a particular length of the waveguide for different bandwidths. And you see that it has a very strong distortion because of the photon wave packet change. Now we put here a little bit of chirping and a little bit of chirping here, and that compensates the curvature of the dispersion relation, and we go down to this much better, this is the depletion of the qubit, but it's a proxy for the fidelity of the state transfer. Can we do better? Yeah, but the problem is that we are in a limit where we are introducing this chirping, and the Markovian theory as showed, it doesn't really work. We can improve the Markovian theory by introducing corrections to the memory function, and you get first and second order derivatives. That means you go from an equation like this, where you have perfect decay, to equations where you get some renormalization of your dynamics. And this gives you another order of magnitude, but going even further becomes more complicated. So you will need to really do some other approach, like quantum control, to go even further than that. But that's not a bad number, 10 to the minus 4, 10 to the minus 5. It's pretty decent for applications in quantum information. So another thing that we can do, as I told you before, is that experiments have multiple cavities. And so all these protocols, all this state transfer engineering can be generalized to different chains of bosonic media. So this would be a very wild guess where you put the cavities here and you try to use the usual controls. And you find that because you have two cavities, there is a resonance there that prevents the depletion of your qubit. So you don't get any useful transfer. Now you do this chain cascaded differential equations and find out what is the control to produce a certain photon. You go down here, and then you distort the photon to compensate the dispersion relation, and you go down here. So it's a very scalable, very easy way to operate with these systems, and we have full control of it. So it's so good that you can now think about it as one more primitive. You have your distributed quantum computer, and now you can shuffle qubits back and forth. So in principle, you can use this to do distribution of entanglement or distributed quantum computation. You take one qubit from one place, bring it to another, do a gate, bring the qubit back, and suddenly your system is entangled. That's basically where we could stop here for the engineering approach. Let's try to do some physics. So we can try to do a little bit more of quantum optics experiments to see how we can begin to establish interactions between these systems. One thing that Ricardo Puebla and Guillermo, these are the two guys who I'm working with on these projects, decided is that they wanted to find out how they could use the possibility of not depositing one photon, but depositing fractions of a photon. And if you have this possibility, which is simply just changing the control you have, you can begin to think about protocols where you can distribute fractions of a photon across networks and use this to distribute entanglement in a very clever way. You create W states that are a source for your system. You can distill them and use them in different protocols. The idea is not very difficult and simply reusing the calculations I showed you before. Another interesting thing is that we could avoid this kind of approach that requires perfectly synchronizing your insertion and absorption controls, which is very challenging experimentally, especially if you have very long waveguides, and try to be more passive. And the idea would be, I'm going to keep some nodes in a dispersive limit, where my qubit is slightly detuned from the filters that connected to the waveguide, and I'm going to use only other nodes to inject photons and retrieve them and try to distribute entanglement. The approach is very simple. It's based on something that has been demonstrated experimentally many times, which is the fact that if you send a photon to a cavity where you have a dispersively coupled qubit, this photon can be scattered with a phase shift that recognizes the state of the qubit. There are many theoretical proposals and experiments in many places, like for instance, the group of Nakamura, where they have really shown these collisional phase shifts. And they are very strong. It's a pi shift that can make you a quantum gate. So basically, you have two qubits living in two different nodes. One of the qubits is mapped to a photon. The photon collides with the second node, gets a phase shift, and is reabsorbed in the first node. This is a passive protocol, doesn't require any synchronization. And if it works, in just one step, you can entangle a whole array of nodes, because it's basically the gate for doing cluster states. So we've shown that it's possible to do that. Essentially, this will be the scattering phase that you get for a photon that is, can be either on resonance or off resonance from a cavity. When you have a qubit, the resonance is moved to the left or to the right, so you get these opposite phase shifts that have a pi difference. And we verified it both analytically and numerically for the kind of wave packets that we can create. The only problem with this protocol is that if you look at this scattering phase, it has some curvature. And this curvature is very similar to the curvature the photon sees when it propagates to the waveguide. So the photon, when it collides with the cavity, it's reflected back with a -1 sign, but there are slight quadratic contributions that are frequency dependent that change the shape of the photon. So you have to be perfectly monochromatic for this to be ideal. So this creates a compromise. So if your photon is very long, the phase shift is perfect, but suddenly the process of emission and absorption of the photon are confused with each other, and it doesn't work so well. And if the photon is too short, then you get this not correctable dispersion of a phase that occurs because of the collisional process. So there's an optimum here. We believe that this can be improved by moving towards here and doing some kind of quantum control approach where you can merge the emission and absorption of the photon in a single dynamics that we cannot really right now model with these tools. The other thing that we have been looking at is to increase the dimensionality of these things by having more photons and more qubits. There are many natural approaches to do this. One would be time beams, to time your protocols so that you can send qubits one after another. That's a little bit trivial, not need any more quantum optics. But the other two more interesting protocols are to use different colors, or different colors and different shapes, orthogonal modes for this. This second part, it comes natural from the inverse process I described before, where we can really engineer the photons we want. If we could do that, we can both optimize the channel capacity, we can send more qubits. We can also begin to think about sending entangled states, multi-qubit entangled states from one place to another. Or from quantum information applications, you can begin to think about doing error correction. So if you use more qubits to encode a logical qubit, the channel becomes very more robust with just a very cheap improvement in the protocols. So as I said, the modes can be engineered. We can send photons with different shapes. We simply have to change the control. And we can do that both in phase and amplitude. That works. And we can indeed do perfect transfer with all types of modes. And if you send one mode and use the wrong control, it's rejected by the second node, so that selectivity is achieved. The problem in practice is that you cannot do this insertion or state transfer simultaneously with multiple qubits operating in orthogonal modes. So they disturb each other. That doesn't work. So the more clever approach would be to also detune the qubits so that they are progressively separated in more and more in frequency space. This is what you see here. This will be the fidelity of a state transfer for 2 photons from this node to this node for progressively larger separations between the qubits. And you see that as you increase the separation, the infidelity decays, and you reach a limit, that is the limit of infidelity of sending just 1 qubit. This curve you see here, this will be the simulations, exact simulations for 2 photons, perfectly overlap with what you would expect, which is the overlap between the photons that are set at different carrier frequencies. So it's a very simple idea, but with this in mind, we can suddenly think about how many qubits you can send. You can do a pessimistic estimation of the infidelity by looking at all the possible crosstalk between the photons, and we get this kind of curves. So depending on what is the separation between the photons in terms of the bandwidth, we can see that you can have very good total error with up to 100 qubits in the system. In practice, you are limited by the setup. So if you have different number of photons, you are using more and more bandwidth, and that's something that can be experimentally challenging. And in some cases, like in the case of the 30-meter waveheight, we saw that up to 10 photons is okay, but more than that, we cannot really fit in the experiment realistically. So that's basically what I wanted to say. So we have a new platform in many forms. This is one form, which is very nice because you have also really spatial space-like separation, but we have different avenues to go to. One will be more like quantum information, where we have connected quantum computers and scale-up quantum systems. This is also a tool for connecting quantum devices. So eventually your quantum computer will be connected to quantum sensors or other things. So understanding these quantum links is useful from a just purely quantum engineering approach. So I think that that's doable. And for us, what is more interesting in the future is to really think about how we can put qubits and let them interact with this new media, where we have both the flexibility of achieving very complex interactions between these qubits, arbitrary form interactions all-to-all, and also introducing the retardation of these interactions as a new knob that is opening new physics. And well, I think that I'm running out of time, so I had other things to tell, but I will stop here, and yeah, thank you. And that's a little advertisement. There is a new journal on quantum technologies. If you want to contribute, you're more than welcome.
All righty, so we have time for questions.
When you were correcting the chirping, that you were writing an equation and I didn't get it. You have like the derivative of v, but then it also appeared on the other side.
So what happens is that if you look at the equations I wrote initially, we are not using input-output here. We're using these memory functions of the waveheight. And the usual approach is that these are delta-like functions. And so basically, you only you don't see the dynamics of the qubit. You take it out of the integral. And that gives you the decay rate of the system. If you have chirp couplings, then the chirping that you have here means that you cannot do that approximation. So you need to do the second order approximation. That is simply integration by parts. And when you do integration by parts, you get the time derivative of your qubit. And that renormalizes the equation. It's like an average change in the frequency in practice. It doesn't give you perfect fidelity. To do it better, you would need to go to higher orders. So, yeah.
Now I understand. Okay, thanks.
Okay.
Well, actually, I sort of have a follow-up to that. As someone who has dealt with superconducting waveguides, they often have, or always have, quite a lot of ripples. So it's not just curvature, but goes up and down. And so I
Yeah.
guess what power of impossible is it to take that back out again?
Yeah, that's a real problem in experiments. If you look at the fidelities that can be achieved in this setup, I think they are limited in a large way because of that. You have first to get very good impedance match to the waveguide, and that in this case is challenging. And then you may risk having internal reflections or resonances that you don't want. If it's just a matter of not of resonances, but just distortion, further distortion, I think that can be compensated. But if it's really something that can create pseudo modes around there, that can be challenging. And these are things that can spoil the fidelity of transfer.
Like, what sort of bandwidth would these photons have when you go with your ideal protocols? 100 megahertz, gigahertz?
They have couplings of up to 140 megahertz, but I think they explore 20 to less. If you give me an upper bound of the bandwidth, I can do any lower bandwidth that you want by simply changing the coupling in time more slowly. But experimentally, I think they were around 10, 20 megahertz.
Any other questions?
Yeah. So I will be here 1 month, looking forward to discuss about these things with you.
I mean, also, maybe I would ask a follow-up question then, because can you go to the microphone?
Or I can repeat the question.
Many questions. But so one is, have you looked at the Fermi problem in the presence of non-Markovian delay, and does that change the outcome? Also, the contribution of the non-rotating wave terms in that case.
Yeah, we were looking at this with non-rotating wave coupling, when you have to include the counter-rotating terms. And there what happens is that you can get a slightly out of light cone entanglement, very tiny. It's simply the buildup of the correlations between the two qubits that then goes up to the highest value when the photons really hit the qubit. That's a very tiny value. Also depends on what models you use for the field, but yeah, we have looked at it in the ultra-strong coupling limit.
How does it change when the separations go in the non-Markovian regime?
No, this is what I mean. You have a light cone, and there is like a wave front to the light cone. A very short time, very small values begin to pop up slightly outside of the light cone. And yeah, these are delicate calculations. It depends a lot on what models you have here. In principle, this comes from the fact that if you have localized perturbation in the Schrödinger equation, it immediately spreads to the whole space. And that can be realistic or not, depending on what you look at.
Thanks.
Welcome.
So have you considered some other states in this transport? I mean, some GKP states or some CAT state, these kind of...
Yeah, these are qubits. So if you look at the connection, it's one qubit connected to a cable. There have been, well, actually, one of the first experiments superconducting circuits was with cavities. So they converted the state of the cavity to a waveguide. The problem when you have this kind of tunable couplings, and I think Klaus Mormer has some series of work on that, is that you have nonlinear terms in the coupling that make your capacity to inject arbitrary numbers of photons less good. So in principle, maybe the first photon travels nicely, but the second photon sees a nonlinear shift, and then the state is distorted. So we haven't explored anything that is of dimension greater than 2.
All right, okay, thank you.
Maybe I'll ask another evil experimentalist question. So these superconducting waveguides are in some sense very low loss, but they typically suffer from a fairly bad insertion loss at the input and from really gross dispersion relations, actually.
Yes.
and then the sheer amount of technology required to keep one of these things cold, so that, that 30-meter cable. And so I guess this is much more of like an open-ended question that, the cooperativities are really nice in the superconducting, but somehow the waveguides are really gross and expensive. And so, the trade-offs between optical photons and superconducting somehow just very open-ended. What are your thoughts?
I think insertion loss is a problem in this setup in particular, so they need to change the connector, because that's a huge percentage of the fidelity. But I'm not an experimentalist, this is what I learned from them. It's true that, this physics is very challenging because of the size. The size in this particular scenario is more related to fundamental questions about quantum mechanics. So can you do entanglement to these distances and then see that there is no local realism that can explain that? But the same physics could be explained or explored in smaller length scales if you can have slow waveguides. And we had seen, Hannes mentioned some experiments from Oscar Painter where you can have a slow light in a waveguide, and that could be another way to explore this kind of retarded interactions and even do networks with this kind of waveguides. I think that's another interesting approach, and there are many high impedance devices now are coming out in different experiments that could be repurposed for those things. That physics would be immediately what I said before. It will be more on the physics part, not on the network part. Then the network part is in itself a goal. Do whether you want to do it with superconductors or not, it's open for debate. I think one nice thing about these superconducting setups is that they are already working and they have extremely strong coupling. And to do the same thing with IMO setups is challenging. So this would be a very nice playground to learn about how to build quantum networks, how to do the protocols, how to do improve state transfer, how to do all these kinds of things before we move to other platforms, which you probably could do with transductions more easily for longer distances.
Okay, any last questions? Going once, going twice? Okay, so then let's thank Juanjo again.
Thank you.